Good morning, everybody. Today we will continue with conservative and non-conservative forces. So first of all, we will learn what is the difference between conservative and non-conservative forces. Then we will learn how to deal with these non-conservative forces in terms of energy. And we will finish with the force-energy relation and energy diagrams. So let me start with the conservative forces. So, for example, gravity and the spring force. Here we have a spring, and this spring applies a force in this direction on this mass, let's say. So this spring force and also the gravity are conservative forces. So what is the main property of a conservative force? That they allow conversion between kinetic and potential energy. Okay? This is very important. If we have a conservative force, then it allows conversion between kinetic and potential energy. Look at this one, spring force. Let's consider that the spring is staying here. We store potential energy. Okay, now at this initial position, we stored potential energy in the spring. And then when we release this one, this stored potential energy is converted to the kinetic energy. Okay, now this mass is moving with some certain velocity. Then this spring force allows us a conversion between kinetic and potential energy. What about the gravity? Look at this one, this picture on the right side. Here we have a mass. This is the weight. And let's consider this box at the beginning is staying here at rest, and it has certain height and it has certain potential energy. Okay, whenever we release this box, it is moving down, and the potential energy due to the gravity is converted to the kinetic energy. Then the box has certain velocity. Or let's consider that at the beginning, box is staying on the ground, okay, with zero potential energy. And then I am moving this box in this direction with certain velocity, and I stop here. So during movement, I have kinetic energy, and I spend this kinetic energy to store potential energy. And this potential energy is used to produce kinetic energy during movement from this position to down. Okay, here also same. So I apply certain force to the right side on this mass, and then I pull this mass to the right side, and then this mass will have certain kinetic energy, and we will store potential energy in the spring, and then this potential energy will be used to convert it to the kinetic energy during this type of movement to the left. Okay, so this is the conversion between kinetic and potential energy in conservative forces. But in case of non-conservative force, for example, friction force or fluid resistance force, these forces are called as dissipative force. What is the meaning of dissipative force? So you lost something, okay? You lost energy. So in non-conservative forces, you cannot store potential energy, but they do change the internal energy of a system. We will discuss this one in the forthcoming transparencies. So if you have non-conservative forces, for example, friction force or fluid resistance force, we cannot store potential energy, but change the internal energy of a system. Let's consider that here, the same spring and also mass. Here, and let's consider that this is the equilibrium condition. X is equal to 0, okay? And let's consider that this is at rest. Whenever I release this mass, there will be F spring to the left side. F spring to the left side, okay? And this spring at the beginning has some certain potential energy, which is given with 1/2 kx square. X is this distance. Okay, And when I release this mass, this potential energy will be converted to the kinetic energy. But if we have a friction between these two surfaces, then there will be a kinetic friction here, let's say. So some part of the potential energy stored at the beginning here in the spring will be converted to the kinetic energy, and some part of energy will be dissipated, will be lost due to the friction force. So where this energy goes? The energy goes to the internal energy of the system. What I mean, during this friction, the surface of this box and the surface of the ground here will be hot, okay? So the temperature of this mass and the temperature of this surface will be increased. So the energy will be spent to increase, to change the internal energy of the system. Okay, we will discuss all the things within this lecture. Do you have any question here? Okay, then let me discuss the properties of conservative forces. Here we have an example. There's a guy, and this guy has initial position is this one. This is the sea level, and this is the initial height of this guy from the sea level. And this is the final height of this guy from the sea level, let's say. Okay. And let's consider that this is the 0. So due to the gravity, there is a weight acting on this guy, okay? And this guy can have 3 paths to reach to this second position. One path is shown with the blue color. So it is like this. Then he reaches to this point. Another path is this one. Okay, then he can reach to the second position. Or there is another way, shorter one. He can reach to the final position here. But what about the work done by gravitational force here? The work done by gravitational force is same for all 3 paths because gravitational force is conservative. Okay, so the work done by a conservative force such as gravity depends on only the endpoints of a path, not the specific path taken between those points. And this work done by the gravity does not depend on the path taken. So now we have 4 properties of conservative forces. Please be careful with this ones. The work done between 2 points by any conservative force, it can be spring force, it can be gravity. Okay, we are talking about conservative forces. It can be expressed in terms of a potential energy function. Okay, remember the potential energy due to the gravity, mgy. Okay, here mgy1, here mgy2, and remember the spring. Let's consider this is the equilibrium and this is the F spring. So F is given with minus kx, right? And what about the potential energy? Potential energy is given with 1/2 kx squared. So if you have a conservative force, then you can express it in terms of a potential energy function. It is reversible, okay? So you can convert potential energy to the kinetic energy, and you can convert kinetic energy to the potential energy. So if the total mechanical energy is conserved. And it is independent of the path between 2 points. And the last one, the work done between 2 points is 0 if the starting and ending points are same. Okay. For example, let's consider that. Let me choose another color here. Let's consider that this guy here on the left side starts from this initial position and follows that path and then reaches to this second position and then comes back. Now it has final position, but this final position is the initial position. Then the work done between 2 points is 0 if the starting and ending points are the same. So these are the properties of the conservative forces, and the work done between 2 points by any conservative force should have these properties. Now let me continue with the example from the book, example 7.10, frictional work depends on the path. So then you will better understand the mechanism, you will better understand the topic. Here, there's a table, very heavy table, and here there's a futon. You are rearranging your furniture and wish to move 40 kilogram futon 2.5 meter across the room. So you would like to change the position of this futon. It is staying here at the beginning. And now you would like to move it to the point 2. Okay. A heavy coffee table which you don't want to move. This one here, there is a heavy coffee table, blocks this straight line path. Instead, you slide the futon along a dogleg path. Dogleg path, this one. So this is the easiest way, but since there's a table here, you have to move in these directions, okay? So the doglegs are 2 meter and 1.5 meter long, 2 meter, 1.5 meter long. How much more work must you do to push the futon along the dogleg path than along the straight line? The coefficient of friction, kinetic friction, mu k is this one, 0.2. So question is, how much more work must you do to push the futon? So now let's have a look at the question. What about the kinetic energy of the futon here? Kinetic energy of the futon here is 0. What about the kinetic energy here? It is 0, okay? So at the beginning, kinetic energy is 0 because it at rest. Finally, kinetic energy is 0 because it at rest. So there is no potential energy change here because the position, y position of the futon is same. So, and what about the elastic potential energy? There is no spring here. So the total potential energy here at the beginning is 0. And final potential energy here is 0. Now, let's write the formula which we have learned during the last lecture. K1, initial kinetic energy plus total potential energy of the system includes potential energy due to the gravity and elastic potential energy plus V other K2 plus U2. So this is 0, this is 0, this is 0, this is 0. So from this expression, you can understand that V other is also 0. So what about the V other? So what kind of forces do work here? We push this photon, okay, and then we have some certain displacement, okay, then this force, push force, to work on the photon, and in addition to that, there is a friction force, which is opposite to this push force. This is kinetic friction force, okay. From this one, you can understand that the work done by push force is equal to the negative sign of the work done by friction force. Okay, here we have it. Let me clean this part. So since V other is 0, because this one here, this one, this one, this one, all of them are 0, then V other is 0. Then what we have within the V other? Within the V other, we have this ones. V other, VU, push force, you apply force on the photon, plus the work done by the friction. And it is 0. Then you can get this expression. Okay, so what about the friction force? Friction force can be written with this form, mu k times n, and n here is given with mg, okay? If you write the forces along the y-axis, you can find this expression. Then, finally, look at this solution on the right side. Work done by yourself, which is equal to minus work done by the friction force. And here we have minus. And what about the work done by friction force? It is negative because it is always opposite to the applied force. Then here we have minus Fk times S. What is this S? This S is displacement, okay? So what was the question? How much more work you must do to push the photon along dogleg path than along the straight line path? So you can move this photon in this direction, and displacement is 2.5 meter, or you can move this photon in dogleg path. Okay, now you have more displacement. Okay, instead of S, you will put different numbers. So this is the work done by yourself. Here we have mu k, which is given in the question. Here we have mg, m here, g is here, and this is the displacement S for the straight line path along this path. Okay, and instead of straight line path, just use this dogleg path, 2 meter, this one, plus 1.5 meter. Now this is the displacement. Now we have another work. What do you see here? If you move this photon along a straight line path, then the work done by yourself will be equal to 196 joule. But if you follow this dogleg path, then the work done by you is equal to 274 joule. Any question here? Okay, now let me continue with example 7.11, conservative or non-conservative. So there will be a force, and then we will decide that this force is conservative or non-conservative. Here we have a question. In a region of space, the force on an electron is given with c times x, j, where c is a positive constant. The electron moves around the square loop in the xy plane. Look at this figure here. This is the x-axis here. This is x-axis. And this is the y-axis. The electron moves around the square loop in the xy plane. Okay, so electron follows this path, starts from the origin and then goes in this direction and then follows this square path due to this force acting on the electron. Calculate the work done on the electron by force F during a counterclockwise trip around the square. Is this force conservative or non-conservative? This is the question. We can use the equation here. Why? Because force is not constant. What you see here, there is a constant C, but here we have X. So depending on the X, F changes. Okay, so you can consider like this. This is the x-axis, this is the origin, and here at the origin, F is C times, instead of X, you will put here 0, J. Then at the origin, force is 0. Let's consider here X is equal to 1, then write the force. C times 1 times J. Okay, from this expression, I am writing this force values. So if X is equal to 2, then force can be written C times 2 times J. Okay, so force changes. Force is not constant. Okay, it is non-constant force, but I don't know whether it is conservative or non-conservative. I will look for this one. So the work done by non-constant forces can be written in this form, which we have learned during the last lectures. Okay, this is the integral from initial position to final position. This is the non-constant force, and this is the infinitesimal displacement, dl. Okay, now let's apply this one to calculate the work done by this force on this electron. But first of all, let's try to calculate FDL for each leg. Here we have leg 1. Let me choose another color. Here we have leg 1. Electron moves in this direction. And then here we have leg 2. Electron moves in this direction. Here we have leg 3. And here we have leg 4. Okay, and here we have leg 1. So just try to calculate FDL along these legs. Start from the first one. On the first leg, from 0, 0 to L0, this is X, this is Y. This is X, this is Y. Okay, look at this one here. X here at this position at the origin, X is 0 and Y is also 0. Okay, and here at this position, X is equal to L, length of this path, and Y is equal to 0. Okay, here look at this one. X is equal to L and Y is also equal to L. Look at this position. X is equal to 0, Y is equal to L. Okay, so these are the positions on the corners of the square. Then I will calculate this FDL. So what about the direction of the force? Look at this expression. F is given with this expression. Constant number, X times J. This is the unit vector along the y-axis. So the F force will be always along this direction, and it is non-constant, okay, because X changes. So look at this square here again. At the beginning, force is 0 because here X is 0 in the force equation. And here I have certain force due to the certain number of the X, but direction is given with this J unit vector. Then the direction of the force is along the positive Y. direction. And here I have bigger force, and here I have bigger force, which is given with C times, instead of X here, just you can use L, because here at the final position of the first leg, X is equal to L. Put L here, then again direction along the positive Y direction, okay? Then I have this type of force here. So now if you come to this point, again F is this one, but since the X is decreasing along this path, so F also decreases, but its direction again along the positive Y. Okay, now I know the direction of the F, I know the magnitude of the F on this graph. Okay, now let's try to calculate this one, F times dl. This is scalar dot. So at this first position from the origin to this one, when the X is equal to L, what about the F times L? F is along the positive Y, and dl, here we have dl, displacement, is along the positive X. So the angle between dl and the F here is always 90 degrees along this leg 1. So then this scalar dot will be 0, okay, for this leg 1. Then the work done on the first leg is 0, because this term will be 0 here, since they are perpendicular to each other. So what about the work done here? What about FDL along this path? F is given with CLJ, and here we have DL. What about DL? DL is a displacement along the y-axis, but very small, infinitesimal displacement. So instead of dl here, I can show dy times j unit vector. So this is the displacement along the y-axis, and j is showing the direction of the displacement. So here we have j unit vector dot another j unit vector. It will be 1. And then finally, this FDL will be equal to C times L times dy. And the work done by this force along this leg 2 can be written by using this expression. So this is V2, work done on the second leg by this applied force is equal to the initial position. Initial position is this one along this path. I'm dealing with leg 2. Initial position is for X is L, Y is 0, and this is the final position. Both X and Y are equal to L here. So these are the integral limits from L0 to LL, FDL. I have already calculated FDL. Put this FDL here. And the integral over y. So here, what about the limits for the y? Here I have 0 and here I have L. Take them here. So instead of the L integral, now I have the y integral and the limits for the y. So then if you solve this integral, you will get the work done on the electron along the second leg is given with CL square. So what about the work done here on the third leg? Since force and dl are perpendicular to each other along this leg 3, so the work done on the electron along this path is 0. And here, again, we have what we have here. What is the force here along this last leg, for leg 4? Here, force is 0 because we are staying at 0. If x is 0, force will be 0. So along this leg, this last pass, the force is equal to 0. Since the force is 0, then work will be 0. So I have only work on this pass along the leg 2. So then the total work done by F force on the round trip is written with this form: W1 plus W2 plus W3 plus W4, and all of them are 0 except the work done by the force along the leg 2. Then the total work is given with this expression. So now what was the question? Is this force here conservative or non-conservative? So look at the effect of the force. Due to this force, electron starts from this one and goes along leg 1 and goes along leg 2, goes along leg 3, and then it goes back to the initial starting point. So if the object goes to the starting point, the work done by the conservative forces must be 0. Here we have discussed the work done between 2 points by any conservative force is 0 if the starting and ending points are the same. But here the work is not 0. Then it means that this force applied on an electron is a non-conservative force, okay? And it cannot be represented by a potential energy function. Any question here? Then let me continue with conservation of energy. Be careful here. The mechanism is very simple, but you must concentrate on the topic. Non-conservative forces cannot be represented in terms of potential energy. I have already discussed this one, but we can describe the effects of these forces in terms of kinds of energy other than kinetic or potential energy. So what I have told you in the first transparency of this lecture, the non-conservative forces are also called as dissipative forces. They spend energy, and this energy cannot be converted to the potential energy or kinetic energy. But this energy can be dissipated as an internal energy of the system. So here I have an example and you will better understand. So let's consider that there is a car, and let's consider this car is moving in this side with some certain velocity, with some certain kinetic energy. Let's consider that height is 0 here and potential energy is 0. So potential energy of the car, gravitational potential energy of the car is 0. It has certain velocity. Due to the velocity, it has certain kinetic energy. Okay? After certain distance, the car stops. Okay? Here, now V2 is 0, final velocity. So kinetic energy is 0. So at the beginning, potential energy was 0. So here, I'm talking about a straight line. So there is no change in the y position, then gravitational potential energy is again 0. Okay? So here at the beginning, I had kinetic energy, but in the final case, I don't have any kinetic energy. So what happened to this kinetic energy? Where has it gone? The kinetic energy is spent due to the friction force. So due to the friction force between the surface of the tires, when you lock the brakes, okay, to stop, this surface of the road and this wheels, the rubber of the wheels, okay, or rubber of the tires will be very hot, okay, due to the friction. So this kinetic energy will go to this rubber tires and also to the road to increase their internal energies, to increase their temperatures, okay? This kinetic energy is spent to increase the temperatures of the road and rubber tires, okay? So then what happens? the energy associated with this change in the state of the materials is called internal energy. So you increase the internal energy of the rubber tires and you increase the internal energy of the road. So this kinetic energy is now 0 at the final position, but this kinetic energy is spent to increase the temperature of the tires and temperature of the road. And this process is irreversible. You cannot get this energy back to increase the kinetic energy of the car. Okay, for this reason, friction force is called as non-conservative force. So here again, the same information. Rising the temperature of a body increases its internal energy. Lowering the body's temperature decreases its internal energy. Okay, non-conservative forces, for example, friction force or air resistance, fluid resistance, do not store potential energy, okay, but they do change the internal energy of a system. So just remember the spring. This is the x is equal to 0, equilibrium condition for the spring, and here I have a mass, and then I have applied a force, and due to this force, this mass has certain velocity and kinetic energy. Okay, now this is the final position. So with this force, I can able to elongate or stretch this spring up to this point. Then I fix this box here. Then all this kinetic energy is converted to the potential energy here, which is given with 1/2 kx squared. I have converted this kinetic energy to the potential energy. Whenever I release this box, it will go back, okay? Then this potential energy will be converted to the kinetic energy again. So in the spring force, also in the gravity, you can convert kinetic energy to the potential energy. You can convert potential energy to the kinetic energy. But in case of non-conservative forces, for example, friction force, the energy of the system is spent to increase the internal energy of the system. Here, as I explained in the car. Okay, any question here? Then let's get the final expression for the conservation of energy. Careful experiments show that the increase in the internal energy is exactly equal to the absolute value of the work done by the friction. Absolute value of the work done by friction. In other words, V other here, the work done by friction, is equal to the change in the internal energy of the system. Remember the formula for the work done by gravitational force is given with the change in the potential energy, gravitational potential energy. And remember the work done by elastic forces is equal to minus the change in the elastic potential energy. So this is same, okay? The work done by non-conservative forces is equal to minus the change in the internal energy of the system. You can write it like this. The other can be written like this, minus delta U internal, okay? So the work done by non-conservative force like friction is equal to the change in the internal energy of the system. So now within this expression, remember this expression, V other U2. What we have within U1 and U2, within U2 U1, we have both gravitational potential energy plus elastic potential energy. Okay, don't forget this one. So instead of V other, you can use this expression minus delta U internal energy. Okay, so the change in the internal energy of the system. What is the meaning of internal energy. Internal energy is the temperature of the system, okay? So you change the temperature of the system, as I explained in the previous transparency. So remember that delta K is given with K2 minus K1. Here we have K2, here we have K1. Take this one to the right side. And here we have U2, here we have U1. Take this one to the right side. And delta U is given with U2 minus U1. And finally, you will have this expression, delta K plus delta U plus delta U internal are equal to 0. So what is this? The change in the kinetic energy, the change in the potential energy, the change in the internal energy. So they are equal to 0. This is the law of conservation of energy. So what is the physical meaning of this one? Let's consider that there's a car here and it is moving along this type of path. This is the initial position of the car. This is the final position of the car, okay? Initial position, final position, let's say. And let's say there's a difference here. Maybe I should draw like this. Let's consider this is Y, okay, between these two positions. And here, the car is at rest. K1 is 0. Here, we have some certain kinetic energy, which is different from the 0. And let's consider that there is a friction on the surface. Okay? So, then what about the energy conservation? So, delta K, look at delta K, the change in the kinetic energy. It goes from K1 to K2. At the beginning, it was 0. Now I have certain kinetic energy here. What about delta U gravitational? Here, I don't have any elastic potential energy. In the delta U, I only mean the change in the gravitational potential energy. Here I have U1 and here I have U2. Here at the beginning I have U1, which is different from 0. Let's consider this is Y is 0. Then here in the second case, gravitational potential energy is 0. So I have change in the gravitational potential energy. I have change in the kinetic energy. So here there is a friction force between the road and the rubber tires of the car. Due to this friction force, I have V other here. So due to V other, here I have change in the internal energy of the system. So delta U internal, okay? At the beginning, kinetic energy is 0. The tires are cold, the rubber is cold, and after certain time, they got hot, okay? So they become hot, let's say. So we have also change in the internal energy of the system. So then the change in the kinetic energy, the change in the potential energy, the change in the internal energy of the system are 0. So the change here or decrease in this potential energy can be used to increase the kinetic energy and can be used to increase the internal energy of the system, okay? So you cannot produce new energy. You can only use energy to convert it from one form to another form. This is the law of conservation of energy. Any question here? Let's consider non-conservative forces, friction, for example. An automobile tire flexes as it rolls. Non-conservative internal friction forces act within the rubber. Here, this is the rubber material of the tire, okay? So mechanical energy is lost. What about the mechanical energy? Mechanical energy is given with kinetic energy plus potential energy. So if the mechanical energy is decreased, then this decreased mechanical energy is converted to the internal energy of the tire. Then the tires will be hot, okay? So this internal energy causes the temperature and pressure of a tire to increase as it rolls. So whenever these tires are rolling on the surface, okay, so some part of the total mechanical energy is converted to the internal energy of these tires, and these tires becomes hot. Temperature of the tires increases. So if the temperature of the tire increases, then the pressure within the tires also increases. So it is better to check the pressure of the tires before the car is driving when the tire is cold. So now let me give you this example. This is again related to the energy conservation. So here what we have done, the mechanical energy is spent, but where has it gone? It is converted to the internal energy of the tires. Here there is a battery pack within this helicopter. Let's say here there's a lithium polymer battery within this drone helicopter, okay? So it contains this energy. When this energy is used up, the internal energy of the battery pack decreases by this amount. So this is the change in the internal energy of the battery pack here. So you spend the internal energy within the battery pack, and this energy is converted to the kinetic energy to make the rotor blades and helicopter go faster, or to gravitational potential energy to make the helicopter climb. Let me write the conservation of energy. Delta K plus delta U plus delta internal energy are equal to 0. So at the beginning, helicopter is at rest, staying on ground. So there is no kinetic energy. So initial kinetic energy is 0. But whenever I run it, it will have certain kinetic energy. Okay, let's say along this direction, it will have certain velocity. Then it has certain kinetic energy at the beginning. What about the potential energy? When it is at rest on the ground, the initial potential energy of the system is 0. But after certain height, this helicopter has certain height, okay, from the ground, then it has certain gravitational potential energy. And so what do you see here? This delta K is increased, this delta U is increased. So where to find this energy to increase these two energies? So this energy comes from the internal energy of the battery within the helicopter. So you decrease the energy in the internal energy of the battery, then you spend this internal energy to increase the potential energy and kinetic energy of the system. So increase here, decrease here. So as a sum, the change is 0. The total energy of the system is fixed. Okay, this is the conservation of energy. So let's continue with the conceptual example 7.12, work done by friction. Let's turn to example 7.5, in which truckee skateboards down a curved ramp. So here there's a guy, and this is a curved path. Okay, and there is a friction between the surface of this ramp and also this skateboard, let's say. It starts with 0 kinetic energy. At the beginning, velocity is 0, kinetic energy is 0, okay? And what about the potential energy? Potential energy is given with mgr, 0 kinetic energy and 735 joule of potential energy, and at the bottom he has 450 joule of kinetic energy. So at the bottom, he has certain velocity and certain kinetic energy. And at the bottom, potential energy is 0. Okay. And hence, delta K, the change in the potential energy is 450 joule, and the change in the potential energy is minus 735 joule. The work other done by the friction is minus 285 joule. We have calculated this one in example 7.5 during the last lecture. Okay, so the change in the internal energy is this one. So here at the beginning, we have some certain potential energy. Here we have 0 potential energy. Okay, then we have change in the potential energy. At the beginning, kinetic energy is 0 because this guy is staying at rest. But finally, we have certain kinetic energy. For this reason, we have change in the kinetic energy. So kinetic energy is increased, potential energy is decreased. What about the internal energy? Due to the friction between this ramp surface and also skateboard, this skateboard becomes hot. Okay, wheels of skateboard and bearings will be hot, and also this surface will be hot. Okay, the temperature of the surface and also skateboard will increase. For this reason, internal energy of the system will increase, but the change in the potential energy, the change in the kinetic energy, the change in the internal energy will be equal to 0, okay, in total, because this decrease is compensated with this increase and this increase. Okay, this is the conservation of energy. If you put all numbers which you have calculated during the last lecture, then finally you will have 0. Any question here? During the first part of my lecture, we have discussed the conservative, non-conservative forces, and then we can discuss the conservation of energy. We have discussed the internal energy of the systems. Now, we will discuss the relation between force and potential energy. So during the last lecture and also during this lecture, we have discussed that, for example, if you have a gravitational force acting on a certain mass, then I can write this force with this form, minus mg. Okay, if you choose the direction of the negative y downward, then the associated potential energy can be written with this form, mgy, okay? So we have force, and then I can write potential energy like this. Remember the ideal spring, it also applies a force on a body, and the force applied by an ideal spring is given by minus kx, and the corresponding potential energy function is given with this one, 1/2 kx squared. So we have force, we have potential energy. So let's consider that potential energy is given and force is asked. So what to do in these cases? Let me write here. Here, in case of gravitational force, you have force and then you have the potential energy. Here, in case of elastic forces, you have force and you can get the potential energy from this force. So what about you know the potential energy and how to get the force, okay, from this potential energy. So today we will learn this one, force potential energy relation. So let's consider that we have a motion along a straight line, okay, with coordinate x, and then we have x with fx, okay, and then we have potential energy with ux. So the work done by a conservative force equals the negative of the change in the potential energy. So we have learned this one during the last lecture. Remember the work done by gravitational force is given with the change in the gravitational potential energy, right? And in addition to that, work done by elastic force is given with the negative of the change in the elastic potential energy, okay? So the work done by conservative force equals the negative of the change in the potential energy. So let's apply this one to a very small displacement delta x. So what about work here? Work is given with F times S, right? This is force, this is the displacement. So instead of displacement, just use this delta x. Now, just take this equation here, Fx times displacement, which is the work, is equal to minus the change in the potential energy. If I take the force from this relation, then I can get expression for the force. Force is given with negative of change in the potential energy over the change in the position or displacement. If we take the limit as delta x goes to 0, then I can write this expression like this. So here we have a force, and the force is given with the negative of the derivative of the potential energy, okay, minus du over dx. So this is the force from potential energy in one-dimensional motion, only along the x, okay? So here we have potential energy, and if you know the potential energy, and if you take the derivative of this potential energy, then you can get the force, okay, by using the potential energy. What about the meaning of this equation? In the regions where potential energy changes most rapidly with x, this corresponds to a large force magnitude, okay? So let's consider that in a very small distance, in a very small displacement, the potential energy changes a lot, then you have huge forces, okay? A large force magnitude. Also, when Fx is in the positive x direction, Ux decreases with increasing x. I will discuss all these things. A conservative force always acts to push the system toward the lower potential energy. Let me discuss these conditions in the examples in the forthcoming transparencies. So don't forget this one. A conservative force always acts to push the system toward the lower potential energy. Now, let's have a look. The spring force and the potential energy stored in the spring. We have discussed this one during the last lecture. This is the x-axis, okay? This is the equilibrium position when the x is 0. Okay, you can consider like this. Here, there is a spring, and here there's a mass. Okay, this is the equilibrium condition when the x is 0. So the potential energy stored in the spring is given with this expression. If you stretch the spring, then you will store potential energy given with this expression, okay, when the elongation is x. So if you compress the spring in this direction, if you apply force in left direction, okay, along the negative x, then you will compress the spring. The mass is here, you compress the spring, and you store this energy again, okay? This was the potential energy stored in the spring. So this is the behavior of the potential energy in spring as a function of x. So what about force applied by the spring? So the force applied by the spring can be found this relation. So just put here this potential energy formula and take derivative of this with x. Okay, if you take the derivative of this one, then the force can be found minus kx. Okay, now let's have a look graph for F versus X. This is the x-axis, and this is the force axis, Fx. What do you see? If you increase the x, then force increases in negative direction. If you increase the x in negative direction, then force increases in positive direction. So this is the behavior of the force as a function of x. But now let me discuss here something else. Here on the right side, we have spring, okay, and we have certain mass, and we have stretched this spring, and there is a spring force, okay, along the negative x direction, let's say, and we have a displacement. So, and the x is positive here. I have stretched the spring. X is positive. So if x is positive, then force is negative. Why force is negative? Because the direction of the force is along the negative x due to this minus sign here. So what about the force here? This force, spring force, along the negative x direction pushes this box, this body, to the zero, right? What about this zero condition? This is equilibrium. Look at this one. Here at zero, in the potential energy graph, this is the minimum energy, okay? This force, spring force, pushes this body to the minimum energy. Look at this condition. When you compress the spring on the left side, I'm talking about this graph, you compress the spring and then you release the box, okay? Then this spring applies a force along the positive x direction because now x is negative. Here I'm talking about negative x. If you put here negative x, then here I have another negative sign, then the force will be positive. So the spring force is positive. It means that its direction is along the positive x direction, okay? Then this is the displacement. So what happens? This force pushes this body to the zero position, to the equilibrium, to the minimum energy, okay? In both cases, whether you stretch the spring or you compress the spring force pushes the body to the equilibrium condition, okay? Because the spring force is a conservative force, and conservative force always acts to push the system toward the lower potential energy, to the minimum potential energy. So the potential energy here is minimum at the equilibrium condition. So this spring force always pushes this body to the minimum energy. So the same mechanism also valid for the gravitational force. Look at the gravitational potential energy. This is the potential energy axis. This is the y-axis. Okay, I'm talking about the height, okay, position along the y-axis. So what is potential energy due to the gravity? mgy. If you increase the height of the box here, then you will have bigger potential energy. If you decrease the box, okay, down to zero, then potential energy will be zero. If you go further, then you will have negative potential energy. We have discussed all these things, but what about the force? Just use this formula, and instead of potential energy here in this derivation, use this mgy and take derivative of this one, then the force will be given with minus mg along the negative y direction downward, okay? So what about the force? Force due to the gravity is constant. If you consider that g is constant, then we have negative mg here. And what about this force due to the gravitation, due to the gravity? This force always pushes this box to the minimum energy, okay, to the ground. You see, so because this gravitational force is also a conservative force, and a conservative force always acts to push the system toward the minimum potential energy or lower potential energy. So then let me continue with a question here. Example 7.13, an electric force and its potential energy. In physics 2, you will learn many things related to the electric forces and electric charges, and you will use the formula and expressions which you have learned during this semester, okay? The information you have learned during this semester will be more or less valid for the physics 2 and the topics also in the physics 2. So now let me read the question. An electrically charged particle is held at rest at point x is 0. Let me draw. This is the x-axis. Let's consider this is positive x. This is x is equal to 0 origin. This is the minus x, negative x. So here we have a charged particle at this position. And a second particle with equal charge is free to move along the positive x. Okay, let's consider that here we have another particle which is identical with the same charge. Okay, so if it is negative, this one is also negative. If it is positive, this one is also positive, because it says that with equal charge. This is fixed, this charge is fixed, but the second charge on the right side is free to move along the positive x direction. So this charge can move in this direction to the positive x. The potential energy of the system is given with this expression. Ux is given with c over x, where c is a positive constant that depends on the magnitude of charges. Derive an expression for the x component of the force acting on the movable particle as a function of its position. So what is the force acting on this charged particle? So what about the potential energy? What do you see here? This is the x. When the x is 0, the potential energy is maximum, okay? It goes to infinite, right? There is a huge potential energy. If I increase the x, then potential energy will decrease, okay? So you know that the objects like the minimum potential energy, so then they would like to be far away from each other in order to decrease the potential energy. So what about the force? The force is asked, okay? So I have the formula here, which we have learned. This is minus derivative of potential energy as a function of x, okay? If you put this potential energy here in this equation, then if you take the derivative of this potential energy, then finally you can get this expression. The fx is given with c constant over x squared. So here we have the solution of this derivation. The derivative of 1x with respect to x is given with minus 1 over x squared. You know from the derivation of integral topics. I will not go into detail. So then x is given with this expression. What do you see here? If the distance between these two charges, x, is 0, then force is maximum, okay? If you increase the x, then force will be decreased, okay? This is non-constant force, okay? Then we have calculated the force. At the beginning, we didn't know the force. We only have the potential energy, but by using this formula, by using potential energy, I can calculate the force. So now let's try to write this force and potential energy in 3 dimensions. Here, up to now, I have given only the force along the straight line for x-axis. But you can write the same relation also for the y-axis. You can write the same relation also for the z-axis. Okay? Then you can collect them in 3 dimensions. How to do that? This is the x component of the force, y component of the force, and z component of the force, right? So this is the x component of the force, y component of the force, and z component of the force along the x, along the y, along the z, okay? And here I have negative because each component has negative sign, okay? Then what I have here, this one can also be written with minus gradient u. Look at this one, this d over dx I plus d over dy j plus d over dz k can be written as nabla operator, let's say, okay? And then if you use this expression here in the force from potential energy in 3 dimensions, then we can write this expression like this, okay? Then the force is given with minus gradient u. Any question here up to now? If not, let me continue. Now let's apply this information here. And here we have u. It can be elastic potential energy, it can be gravitational potential energy, and it can be electric potential energy, okay? So here I have example with the gravitational potential energy. So the force is given with minus gradient u gravitational. So now let's apply this formula in this example. The greater the elevation of a hiker in Canada's Banff National Park, the greater the gravitational potential energy. So let's consider that one guy is staying here, just the nearby lake, and then he is moving in this direction. Okay, now this is the second position of the guy. So there is a certain height. So the greater the elevation of a hiker, the greater the gravitational potential energy, because it is given with mgh. Okay, if you increase the h, then you can increase the gravitational potential energy. But what do you see here? Here we have this type of wave, okay? And here we have this type of wave. This is steeper than this one. Where the mountains have steep slopes, gravitational potential energy has a large gradient, and there is a strong force pushing you along the mountain surface toward a region of lower elevation. So let me write the expression here, Fy, I mean the weight, which is given with minus du gravitational dy, okay, y component of the force. Here we have only gravitational force and it is along the y-axis, okay? or you can write like this. So what we say here, if we have steep slopes, then this number is huge and the force is huge, okay? There is zero force along the surface of the lake. So here, if you consider that this surface is y is 0, then there will be no gravitational potential energy at this condition. Then the force acting on the object will be 0, okay, along the surface of the lake. Any question? Let me continue with example 7.14. Now let's discuss the force and potential energy in 2 dimensions. A puck with coordinates x and y slides on a level, frictionless air hockey table. Let's consider that there is a table, okay, and there is a puck here, and this is air hockey table, so there is no friction on the surface. It is acted on by a conservative force described by the potential energy function. So here we have a potential energy function in 2 dimensions, given with x and y, which is given with 1/2 x squared plus y squared. So r is equal to square root of x squared plus y squared is the distance on the table surface from the puck to the origin. So let's consider that this is the origin and this is the r, okay, and this is the x and this is the y, okay. Let's consider like this. Find a vector expression for the force acting on the puck and find an expression for the magnitude of the force. So we know the potential energy, but we don't know the force. Then we have to find the force. So how to find the force? You can calculate the x component of the force by taking the x derivative of this potential energy. You can calculate the y component of the force, and then you can get the force here, x component plus y component, and this is the force. So what about the magnitude? X component is given, y component is given. So if you put them here and take the square of them, then you can calculate magnitude of the F. So here you will get this expression, and this is given with R, which we know this one from the question. Or you can do like this. This is the position vector, this one here. Here we have R, position vector, and this position vector is given with x times I, y, j, okay? And then what about F? F is given with minus k times R, okay? And how to get this one? Here we have potential energy formula. What do you see here? X squared plus y squared. What is this? This is R squared, okay? Potential energy in terms of R can be written 1/2 k R squared. So in this equation, just put this one, take the derivative of this for R, then you can calculate this F is equal to minus KR, and you will get the same result. Okay, you can use both methods to calculate the force by using the potential energy given in the question. Any question? Let me finish my lecture with this last part, energy diagrams. It is very easy to understand. Just try to stay on the line, okay? Here we have a glider, and we have a mass, and here we have a track, and here we have a spring, and then we will investigate the energy diagram of this system. What is energy diagram? An energy diagram is a graph that shows both the potential energy function and the total energy of the system. What was the total mechanical energy? Total mechanical energy includes both kinetic energy plus potential energy. Okay, so if you are talking about energy diagram, it should contain potential energy and also total mechanical energy. I will show you here an example. Here we have a glider. This is the air track, and this is the spring, and this is the equilibrium condition, and this is the stretched condition. This is the compressed condition. Okay, these are the limits of the glider. So now what about the energy diagram of this system? Energy diagram of this system is given here. This is the X, and this is the equilibrium condition. This is the maximum stretched position of the spring. This is the maximum compressed position of the spring. Okay, this is the potential energy of the spring. So here at this condition, we have maximum potential energy for the maximum stretching, and here this condition we have maximum potential energy for the maximum compressing. Okay, so an energy diagram shows both the potential energy function and total mechanical energy. What about the total mechanical energy? If the V other is 0, total mechanical energy is conserved. Okay, so it is constant. Total mechanical energy does not change, and it is given with K plus U. So what about the relation with kinetic energy and potential energy? Let me start from this condition. First of all, I have stretched the spring and I store the potential energy. I have maximum potential energy here, but it is at rest and kinetic energy is 0. Okay, I'm talking about this condition. So here, the total mechanical energy is completely given with potential energy, and kinetic energy is 0 because it is at rest. And whenever this glider is released, it will move to the left side with some certain velocity and kinetic energy. Okay, and what will happen? Potential energy will decrease, decrease, decrease. When it reaches to this minimum potential energy, all the potential energy stored at this condition will be converted to the kinetic energy, and here we will have maximum kinetic energy will be equal to total mechanical energy, and potential energy here will be 0. Okay, and in between, for example, here we have some certain potential energy, and the rest of the energy is given with the kinetic energy because glider has certain velocity. Okay, and in each position, the total mechanical energy is given with this relation. If the potential energy decreases, then kinetic energy increases. If kinetic energy decreases, then potential energy increases. But the total mechanical energy is fixed if the work done by other forces is 0, let's say. Any question here? Then let me discuss two important terms: stable equilibrium, unstable equilibrium. Actually, you have learned what is equilibrium. For example, this is an equilibrium condition, but we have another equilibriums. I will talk about this. The topic is very easy to understand. Just try to stay on the line. So here we have force as a function of potential energy. Okay, here we have force given with this expression. And whenever the slope of the potential energy is 0, the force is 0, and this is a point of equilibrium. Okay? If the force is 0, then we are talking about equilibrium. Okay? But we have two types of equilibrium. One is stable equilibrium, the other one is unstable equilibrium. So what about the unstable and stable equilibrium? When potential energy is at a minimum, the force near the minimum draws the object closer to the minimum. So it is a restoring force. This is called stable equilibrium. So let me show you here again on spring. Let's consider that this is the x is 0, very close to equilibrium. Here we have a spring. It is stretched a little bit, and then F spring is in this direction along the negative y, let's say. This is the F spring. Okay, so this F spring would like to push this mass to the equilibrium position. So then this force is restoring force, okay? Restore what? It wants to move the spring to its initial position where it is happy when the x is 0 in equilibrium, okay? So this is the stable equilibrium. When U is at a maximum, when the potential energy is maximum, I'm talking about this condition. This is the 0 position, and this is the maximum stretching of the spring, let's say. Okay, then we have here huge potential energy given with this expression. Okay, the force near the maximum draws the object away from the maximum. So the object is staying here, but the spring force draws the object away from the maximum. This is unstable equilibrium. Okay, this condition is unstable equilibrium. If you compress the spring, just consider this condition. You compress the spring, now it has huge, let's say, potential energy. Okay, then the force applied by the spring again draws the object away from this maximum to the minimum energy condition, and this position also called as unstable equilibrium. I have two transparencies with examples, and then I finish my lecture. So this is an example for the unstable equilibrium. Here there are acrobats, okay, and here you see a single wheel. So each of these acrobats is in unstable equilibrium. What is the potential energy here? Lady has certain weight, and this lady has, okay, so due to this weight, they have potential energy, okay, this is the ground, y is 0, let's say, this is the height of the body, okay, and there is a potential energy was given with mgh, let's say, or mgy. So they have maximum potential energy in this case. Minimum potential energy is here, okay? So the force acting on these acrobats would like to move these bodies to the minimum potential energy, okay? So this position, this maximum potential energy position is the unstable equilibrium. And here there is a graph to better understand the behavior of potential energy and force as a function of x position, okay? And then you will better understand stable and unstable equilibrium. Be careful, this is the last transparency of my talk, and very important in order to understand the energy diagrams in potential energy and force. And what about the potential energy? So let's consider that this is the origin and this is the X position. It can be Y position, okay? I'm talking about straight line motion. So here we have this type of relation for the potential energy, okay? Here I have different points. Now I will investigate what happens at these points. What do you see here? The energy is minimum here, okay? Potential energy here, minimum. And here, potential energy is maximum, okay? So these places are showing us the stable equilibrium where the potential energy is minimum, okay? And here we have unstable equilibrium points are maxima in the potential energy curve. So now let me go step by step. When the energy is E0, this first condition, when the particle is staying at x1, the minimum possible energy is E0. The particle is at rest at x1, okay? And if the energy is here, E1, then the position is between, let me change the color of my pen. Then this new position is this one, okay? Energy is here, and the particle is trapped between XA and XB. XA is this one, XB is this one, and the particle is trapped here if the energy is this one. And if the energy is E2, then the particle is trapped between XC and XD. XC is this one, this condition. XD is this one, this condition. And energy is this one. Then the particle is trapped here. Okay? And if the energy is E3, okay, so this was maximum potential energy, then this particle, if there's a particle within this places, can go out, can escape from the system. So now let me discuss the force, corresponding X component of force due to this potential energy. The force is given with this expression, Fx is given with minus X derivative of potential energy. So now be careful. Be careful when you are plotting the Fx curve from the Ux curve. What about the derivation, negative of derivation here in this range? What about the change in the potential energy? Potential energy decreases in this range, right? So derivative is negative. Here we have negative sign, and then force will be positive. This is the positive side, this is the negative side. Then in this range, potential energy decreases, but force is positive, okay? Force would like to move the system to the minimum energy. And where we have this point, what happens? The energy is fixed here. It does not change. Its derivation is 0, okay? Then force is 0 here. And look at this point. This is the maximum, and there is no change in the energy for a very infinitesimal displacement. The energy is fixed. Then derivation of a constant number is 0. Here, for very short displacement, the energy is fixed, then the force is 0 here, force is 0 here, okay? So there is no force acting on the system at this point. So what about the force between x1 and x2? Look at the slope here. Energy increases in this part, and the derivation of this potential energy is positive, but here we have a negative sign. Then we will have negative force, okay? And here we have negative change in the potential energy, then negative times negative. Here we have positive force. Here we have positive change in the potential energy, then we will have negative force. Here we have negative change in the potential energy. Here we have positive force. These positions are the equilibrium positions, okay? So this is the stable equilibrium. What do you see here? What about the direction of the force? Here, look at this one. Direction of the force is in this direction. Here, direction of the force is in this direction. Here, direction of the force is in this direction. And direction of the force is here. And what about this one? This is the direction of the force. So, in this range, the forces would like to push the system, drove the body to this minimum, okay? The force pushes the body to this minimum, pushes to this minimum. And here, in this maximum energy, force pushes the body away from this maximum potential energy. The force pushes the body from this maximum potential energy. And look at this one. The force pushes the body to this minimum. The force pushes this body to this minimum, okay? And here for this one, the force pushes the system to this minimum. The force pushes the system to this minimum. I'm looking at the direction of the force, which I have calculated here. So then these two maximum energy positions are the unstable equilibrium positions, and these minimums are stable equilibrium positions, okay? Because in the stable equilibrium conditions, forces are pushing the body to the minimum energy condition, and at the unstable equilibrium conditions, forces pushes the system from the maximum potential energy to the minimum potential energy. So you can see that the force always apply to keep the system in the minimum energy condition. Any question here? With this one, I finished my lecture. So take care of yourself. Bye-bye.